Well, hey there, it's your old pal, Mr. Cook, and let's go ahead and do 15 and, 16 and 17, okay? So let's see. In this case, the center was 1. We already got that from here. So I'll use the space down here to um, check the interval of convergence for this thing. Okay, so we've got the ratio test is what we're going to use to figure this thing out. So let's see here. We've got the limit as n goes to infinity, absolute value. And then we have the original sequence in the denominator, so -1 to the n plus 1. And then x minus 1 to the n plus 1 all over n plus 1. And then in the numerator, we're just going to do the same thing, but we're going to add 1 onto all the n's. So it looks like we've got -1 to the n plus 2 now. And then x minus 1, and then n plus 2 over n plus 2. All right. Now let's start simplifying this thing. So let's see. We get limit as n goes to infinity, absolute value. Excuse me. And then we've got two fractions, and one's in the denominator. So we can multiply by the reciprocal. So we get -1 to the n plus 2. And then x minus 1, my bad, to the n plus 2. And then we've got that n plus 2 in the denominator. And this thing is going to, get its reciprocal. And then, so all the stuff that's in the denominator is going to go to the numerator. So I got an n plus 1 in the numerator. And then all the stuff that's like in the numerator of the fraction is going to go in the denominator. So I've got -1 to the n plus 1. And then an x minus 1 to the power of n plus 1. Okay, so let's start simplifying some stuff. Let's see here. I've got a -1 to the n plus 2 and a -1 to the n plus 1. So I'll be able to cancel out all but like one of the -1s in the numerator. And then let's see here. I've got some n plus x minus 1 to the n plus 2. And x minus 1 to the n plus 1. So I'll be able to take out all of n plus 1 from here, leave me just with like one of the x minus 1s, and that'll also be in the numerator. And then the stuff that I have left over, I've got to kind of just leave. I've got an n plus 1 and also an n plus 2. That's the only thing that's left over is that n plus 2 in the denominator. Okay, so here's what's like pretty cool about the limit that we're going to perform here. You can basically treat all the stuff that doesn't have n in it, right? Like you can treat it like kind of like as a constant, as a multiple. And there's this rule with limits where like if you're taking the limit of some sequence, right? As n goes to infinity, if that sequence is multiplied by some constant like 4, for example, and what you can do is you can take that 4 outside of the limit, and it shouldn't affect the limit of the sequence in general. Okay, it's just like a constant gets multiplied on it, so you can like factor it out essentially. So that's what I'm going to end up doing with this. So this stuff right here doesn't have any n in it, right? So I can just like treat it like a constant, like a coefficient. So I'm going to like move that stuff out here, but I'm going to keep the absolute values on it because I don't really know what's going to happen with like that x minus 1. So I'm going to keep it on there just for now. Okay, so like absolute value -1 times x minus 1, and then times the limit as n goes to infinity of like the rest of the stuff, right? N plus 1 and n plus 2. Oops, I don't know why I did a second round of absolute values there. There we go. All right, so what is going to happen to this thing right over here? Well, as n gets really, really big, that top part, if we take the limit as n goes to infinity of n plus 1, that becomes infinity. Well, that goes to infinity. And if we look at the bottom part, the limit as n goes to infinity of that n plus 2, that's also going to go to infinity. So since we have infinity over infinity, we can use L'Hopital's rule. So if we use L'Hopital's rule, here's what we get. I'll go on another line lower. We get absolute value of -1. We're going to get rid of that in a second, by the way. So if you wanted to get rid of it now, you could, I guess, but whatever. So then L'Hopital's rule gives us the limit as n goes to infinity of absolute value of 1 over 1. Well, wait a minute. That's just 1. And the limit of 1 is just, as n gets huge, there's no n on it, so it's just going to be 1. So that just turns into 1. And then here's what's even cooler. Like 1 times that absolute value is just, the absolute value. And here's what's even better. The absolute value, I can take, anytime I'm multiplying stuff, I can take the absolute value of the individual parts. So if I took the absolute value of that -1, it would just kind of get absorbed by the absolute value. So here's what I end up with. Ready? The limit of this whole long thing, so all this crap over here, right? Let me get rid of this. The limit just ends up being the one thing that's left over, which is absolute value of x minus 1. So this whole thing ends up turning into this. It's absolute value of x minus 1. Okay, now since this is the ratio test, we know that this thing is going to converge if the following is true. If this x, like little equation right here, if the limit, that's the limit, if the limit is less than 1, then this thing converges. So we're basically hunting down x values that allow this to happen. So here, that's where we start, right? X minus 1, absolute value less than 1. When it's written up like this is like the perfect format for us because we want to break it down to where it's like x minus the center value, the center number, less than some, radius of convergence. So we know exactly what those numbers are. The center value for x, like the one that will automatically work for convergence, the center value is going to be 1. So we put that in the middle of our number line. The radius of convergence is 1, so we go up by 1 and down by 1. So that puts us at 0 and 2. So we've found our interval of convergence, but we need to check the endpoints. And that's when I'm going to look at the original sequence. The original sequence was -1 to the n plus 1, and then x minus 1 to the power of n plus 1, all over n plus 1. And then, the series around it looked like this. I think it was n equals, was it 0 or 1? We used 1. Okay, 1 to infinity. So something like this. So we've got to check these endpoints here. So let's check 0 first. All right, so we're going to check 0. If we plug in 0 for x, what happens to the series? Well, let's see here. So with x equals 0, we get n equals 1 to infinity of -1 to the power of n plus 1, and then 0 minus 1 to the n plus 1, all over n plus 1. All right, well, 0 minus 1 is -1. And you know what, how I could write this? Like, look at this. It's -1 times -1. Well, -1 to the n plus 1, and another -1 to the n plus 1. So you know what I would do? I would just turn that into -1 to the n plus 1 squared, right? And it doesn't matter if this thing, inside of here is 1 or if it's -1, it doesn't matter because 1 or -1 squared gives you 1. So that means that this whole thing, what I just did when I plugged in 0, it leaves me at the 1 in the numerator, just like that, okay? So now we're going to evaluate this thing. So I plugged in my x value, the endpoint, and I'm going to see if this is going to converge or diverge. So now you go through your little convergence and divergence test, which would be the easiest one to use in this case. I'd probably say that a limit comparison test would be fantastic for this because this one basically looks like this. N equals 1 to infinity of 1 over n, right? And we know that that thing will diverge. And the reason why is because it's a p series. And in particular, the p value is equal to 1. And that's like a rule for divergence for this, right? So yeah, let's see what happens with the limit comparison test. So we're going to use a limit comparison test for this. So limit comparison test says that we're going to take the limit as n goes to infinity, and we can make a fraction out of these two sequences. Because what happens is that if this ends up being like some limit, some constant value, if it's a fraction or a decimal or like a whole number or an integer, whatever, if it gets to a number, right, it means that if this thing diverges, then that means that this thing is going to diverge as well. All right, so let's see if we can do that. So we make a fraction out of these two sequences. It doesn't matter which one you put where. I'll put the 1 over n plus 1 in the numerator, and I'll put the 1 over n in the denominator. Let's see what happens to it. So this turns into the limit as n goes to infinity. And then I'm dividing by fractions, so multiply by the reciprocals. So I get 1 over n plus 1 times n over 1. which is just n over n plus 1. Okay, what happens to this thing? Well, as n gets gigantic, like the top part becomes, infinity basically, right? That would go to infinity. And then the bottom part, the limit, as n goes to infinity of n plus 1, that also tends to go to infinity. So we can use L'Hopital's rule, and we get something real nice. We get, if we do the derivatives for those, the derivative of n is just 1. The derivative of n plus 1 is just 1. So we get the limit of 1, which is just 1. So since this is just some constant, that means that both series will diverge. So if this thing diverges when x is equal to 0, that means that, for this inequality, it stays as a parenthesis, okay? We don't need to change that. So if this was like an inequality, so far it looks like this. It's x values are between 0 and something else, okay? Now let's see what happens when we plug in the other number. Let's plug in, what was the other one? 2. Okay, so now we're going to plug in 2. X equals 2. Gosh. Okay, so I got to rewrite all that stuff. Let's see, negative 1 to the n plus 1. And then it's going to be 2 minus 1 to the n plus 1. All right, let's see if this changes anything up. All right, well, 2 minus 1 is just 1, right? And 1 to the power of n plus 1, well, it's always just going to be 1, so just 1. And 1 times anything is just itself. So now this is going to be negative 1 to the n plus 1 over n plus 1. So now we can, use our alternating series test, it looks like. So this is going to be alternating series test. Or it could be nth term test for divergence, right? So let's see which one it's going to be. Either way, what you need to do is take the sequence, that you get other than the alternating series sequence. So we just take the other part, n1 over n plus 1, take the alternating part out, and we see what happens as n gets gigantic. Well, what happens here is that this thing, as n gets really, really big, will basically tend to 0. It'll become 0. So that's great. We get 0. And if we get 0, that means that it won't be divergent by the nth term test for divergence. So we're going to check to see if it's convergent from the alternating series test. So this is the first step, show that it goes to 0. The next step is to show that it is decreasing. So I would check the nth term, which is n plus 1. And then I would check the n plus 1 term, which would be 1 over n plus 1 plus 1, which would be n plus 2. And sure enough, since the denominator is bigger, that thing's going to be smaller. So both of these things check out. So that means that this thing is going to be convergent by the alternating series test. And since it's convergent by the alternating series test, that means that we put like a bracket symbol right there. And that means that we include the number 2 for convergence. Okay, so there's number 16. I think that's good. That's a kind of longer video. So hopefully that explanation is pretty good. Let's do the last one, number 17, and another one. All right, see you then. Bye-bye.